3I Atlas is passing near the Sun, and something unexpected has just occurred. For the third time in history, a visitor from another stellar system traverses our cosmic neighborhood, and this time, it is doing so facing the scorching heat of our star. Its name is 3I Atlas, and in recent days, telescopes around the world have detected something nobody anticipated: a sudden burst of brightness and an emission of gas directed right towards the Sun. Astronomers knew this object was different from the moment of its discovery. Its orbit is not bound to our solar system. It came from interstellar space, traveling for billions of years before crossing paths with us. But as it approached the Sun, observation cameras recorded changes so rapid that scientists from NASA and ESA are still trying to explain them. The images show an intense greenish cloud surrounding its nucleus, accompanied by a luminous jet extending towards the star. No other observed interstellar visitor until now, neither Oumuamua nor Borisov, behaved this way. Why is 3I Atlas reacting in this manner? What do its components reveal about the worlds that exist beyond our own? And most importantly, what is it telling us about the secrets of the Sun itself? In this video we will explore everything astronomers have discovered so far about the closest approach of 3I Atlas to the Sun and the surprises it left in its wake. In July 2025, an automated observation system in Chile detected a faint point of light moving unusually among the stars. It was the Atlas telescope, and what it recorded was not a common comet. Soon, orbital calculations confirmed something astonishing. Its trajectory was hyperbolic, meaning it came from outside the solar system. Thus the name was born, which now resonates in observatories all over the world. 3I Atlas, the third interstellar visitor in human history. Since then, its journey has been tracked with precision. Unlike comets born near Jupiter or in the Oort cloud, this object moves at a speed impossible for bodies gravitationally bound to the Sun. Its destiny: an extreme close approach to our star, sufficient to test its structure and reveal its composition. Now, at the peak of its perihelion, the point closest to the Sun, the cameras of Hubble, the James Webb, and a network of terrestrial telescopes observe as 3I Atlas releases jets of gas and dust in unpredictable directions. Scientists are trying to understand what forces are acting upon it and why its behavior differs so much from that of Borisov or the enigmatic Oumuamua. This video brings together all the data confirmed so far, captured by NASA and ESA, and the conclusions that are changing our understanding of the objects that travel between the stars. Before we dive into the explosive brightness surge of the interstellar comet 3I Atlas, which skyrocketed the instant a coronal mass ejection, the biggest solar blast in decades, slammed into it head-on, you need to do three things right now so this bombshell reaches every astronomer on Earth. First, smash that like button now. Every like is a rocket that blasts this discovery to thousands of telescopes. Second, hit subscribe plus turn on the bell. The next 48 hours are critical and you'll get real-time alerts the second JWST or Hubble catch the next eruption. Third, scroll down to comments and type interstellar. That keyword instantly enrolls you in the global registry of witnesses watching a comet from another star that may be reacting to solar bombardment. Do it now. Now, let us observe together the most mysterious visitor of 2025, 3I Atlas, facing the Sun. On the 1st of July 2025, as dawn covered the hills of northern Chile, the Atlas system, the Asteroid Terrestrial Impact Last Alert System, registered a faint point moving slowly against the fixed background of the stars. Initially, no one suspected anything extraordinary. Every week, Atlas detects hundreds of minor objects, most of them nearby asteroids or comets with known orbits. However, this point did not fit any pattern. Its trajectory seemed to open outward as if it came from the depths of space. The first photometric measurements showed an extremely faint object, with a magnitude close to 19, almost invisible even to highly sensitive instruments. The astronomers of the Atlas survey sent the data to the Minor Planet Center, which quickly requested follow-up observations from other observatories in Hawaii, Arizona, Spain, and South Africa. Within hours, the numbers began to reveal something unusual. The orbit was not elliptical but hyperbolic. That means its orbital energy is so high it is not bound to the Sun, an interstellar traveler from another region of the galaxy. When the final calculation confirmed an excess velocity of more than 35 kilometers per second relative to the Sun, the news spread throughout the astronomical community. It was official. This was the third interstellar object detected in history, after Oumuamua in 2017 and 2I Borisov in 2019. The number 3I means third interstellar, and Atlas comes from the name of the telescope that discovered it. During the first days, Observers noted that the comet showed a greenish hue typical of the presence of cyanogen molecules and diatomic carbon C2, but its brightness increased irregularly. This suggested that its surface was composed of extremely volatile materials, different from those we see in comets from the solar system. Cosmic radiation, accumulated over billions of years in interstellar space, may have hardened the outer layer, creating a sort of crust rich in carbon and nickel. As observatories began to report their own measurements, the picture became clearer and more mysterious at the same time. The trajectory indicated that the perihelion, its closest point to the Sun, would occur between the 29th and 30th of October, 2025, at an approximate distance of 1.4 astronomical units, 210 million kilometers. It would not pass close to Earth. Its minimum separation would be 1.8 astronomical units, but it would enter a zone where solar radiation can transform any comet. For astronomers, this close approach represented a unique opportunity. For the first time, an object from another stellar system was going to be observed with modern instruments like the James Webb Space Telescope. With Oumuamua, there was only a week of data before it disappeared. With Borisov, the records were limited by its rapid movement. 3I Atlas, in contrast, offered months of tracking and increasing brightness. NASA, ESA, and various European agencies organized a coordinated observation campaign from the La Silla Observatory in Chile to the Gran Telescopio Canarias. All eyes were fixed on the new traveler. The first spectra revealed unusual peaks in infrared emission, elevated proportions of CO2 and CO compared to water. In other words, a comet exhaling different gases, probably formed in a much colder region of its original system. Each piece of data reinforced the sensation of witnessing something that goes beyond the familiar. 3I Atlas did not resemble anything known. Its nucleus, estimated at about 2 kilometers in diameter, seemed to rotate slowly, releasing intermittent jets of gas and dust. The variations in its brightness did not follow the expected pattern, indicating possible scattered active zones or changes in orientation. For scientists, this was not merely a spectacle, it was a window into the formation of other planetary systems. The analysis of the released molecules could reveal the primitive ingredients of other suns. If comets are time capsules of their origin, then 3I Atlas is an interstellar message sent from impossible distances. As data flowed, an inevitable question arose. Where did it come from exactly? Retroactive simulations suggested it entered the galaxy from a direction near the constellation Scutum, traveling at more than 110,000 kilometers per hour relative to the Sun. There is no way to trace its point of origin with precision. It could have come from a dying star or from a young system where planets are just forming. As it approached, conditions changed rapidly. Observatories noted that its coma, the cloud of gas and dust surrounding the nucleus, grew larger than expected for an object of its size. The comet was alive, reacting to the Sun's heat in an unprecedented way. Its intense green color indicated the presence of ionized molecules, possibly activated by ultraviolet rays. Every photon it received was a spark altering its surface. The James Webb teams began preparing their spectroscopic observations for the perihelion. The goal: to detect the most volatile chemical components before radiation disintegrated them. Around those dates, the Hubble Space Telescope also performed a series of follow-up images, capturing a bipolar tail with an almost symmetrical structure, a rare phenomenon indicating activity in both hemispheres of the nucleus. The scientific world began publishing preprints and provisional reports in AR-14 and Nature Astronomy. The titles agreed on one idea: an unusually active interstellar visitor. It was a cautious description, but it reflected the general surprise. Nobody expected such a small object to show signs of activity so far from the Sun. Yet the great moment was still to come. On the 29th of October 2025, 3I Atlas would reach its maximum exposure to solar energy. The sensors of the Solar and Heliospheric Observatory SOHO had already detected a slight fluctuation of dust and gases in its vicinity, a sign that the comet was reacting strongly to the bath of radiation. Astronomers knew something unusual could occur, but no one anticipated the magnitude of what was about to happen. In that instant, 3I Atlas became the most observed object in the solar system. Thousands of people watched live streams from professional and amateur observatories, waiting to see the moment the comet crossed the imaginary line marking the perihelion. The instruments began to register a sudden increase in brightness, greater than predicted by the models. The heart of 3I Atlas seemed to respond to the Sun in an unknown way. That was the signal marking the beginning of a new stage of its journey, a phase in which science would face a series of still unanswered questions about the nature of this interstellar traveler that, for a few brief moments, approached our sun like no other. From the moment astronomers confirmed the interstellar nature of 3I Atlas, attention focused on its orbit. It was an open curve, a hyperbolic trajectory that would never return. Each calculated point revealed that the object had entered the solar system at a speed exceeding 35 kilometers per second and that, once its pass in front of the sun was completed, it would continue its journey into interstellar darkness. Unlike comets bound to the sun, whose routes describe closed ellipses, 3I Atlas came from outside and would exit again into deep space, never to return. Models generated by NASA's JPL showed its gradual approach. First, it crossed the orbit of Neptune, then that of Uranus, and within a few months, it ventured into the region where the Voyager probes once traveled. With each observation, the comet's light showed more evident activity. The distance to the sun decreased rapidly, and the pressure of radiation began to shape its tail. It was like seeing an interstellar traveler awakening under the heat of a star it had never felt before. The orbital trace indicated that its perihelion would occur at 1.4 astronomical units, between the orbits of Earth and Mars. That distance, though enormous on a human scale, is sufficient for the sun to exert a brutal influence. At that point, the temperature exceeds 250 degrees Celsius, and the ice particles covering the nucleus begin to sublimate. The released gases push the surface and create the coma, that diffuse cloud that gives it its ghostly appearance. The transit was followed by dozens of observatories. The European Southern Observatory in Chile, the Lowell Observatory in Arizona, and the Subaru Telescope in Hawaii joined forces to measure its speed, brightness, and activity. The graphs revealed irregular peaks that no local comet had shown before. It was thought that 3I Atlas possessed very uneven active zones, causing its gas emission to ignite in pulses. That variation is key. It suggests the nucleus is not homogeneous but a mixture of materials with different sublimation points, witnesses of another stellar system. Meanwhile, dynamic simulations tried to trace its origin using inverse trajectory models. Researchers from the Harvard Institute of Astronomy and the University of Cambridge projected its route thousands of years backward. The result did not point to a specific system but to an approximate direction. The object came from the Sagittarius arm of the Milky Way, perhaps from a region where young stars are still forming. That possibility excited the scientific community. The material now evaporating in front of the sun could contain chemical traces of an environment totally distinct from our own. As it approached, telescopes registered a sudden increase in luminosity. Between August and October 2025, its brightness multiplied eightfold, an anomalous increase for a comet at that distance. Spectroscopic measurements showed strong lines of CO2 and carbon monoxide, but very little water. This pattern indicated that the composition of 3I Atlas was different from that of comets formed in our solar system, where water is the dominant component. Its place of origin must have been an extremely cold region, perhaps in the outskirts of a distant planetary system where CO2 remains frozen for millennia. The James Webb Space Telescope, with its infrared sensitivity, became a key tool. During September, the MIRI instrument registered the comet's thermal signature as it crossed the 2 astronomical unit mark. The emission curves revealed that the surface of 3I Atlas was covered by a crust hardened by cosmic radiation, so dense that heat barely penetrated a few centimeters. That layer, formed by carbon and silicates, acted as a shield but also accumulated internal tension. Scientists suspected that upon reaching perihelion, thermal expansion could fracture it and release violent jets of gas. Meanwhile, from Earth, amateur observers began to follow its movement with medium telescopes. In the first weeks of October, the comet appeared faint, at magnitude 13, visible only with long photographic exposures. However, calculations predicted it would reach magnitude 8 near perihelion, sufficient to be seen by experienced astronomers from dark sites. Although it would never become visible to the naked eye, its passage promised a first-rate scientific spectacle. During those days, the instruments of SOHO and the Solar Orbiter monitored the region around the Sun. Both detected slight increases in dust and gas coming from the direction of 3I Atlas, a sign that activity was increasing as it approached. It was the direct effect of solar radiation hitting an object that had never felt its heat before. On a deeper level, numerical models showed how the solar magnetic field influenced the comet's tail. The ionized particles of CO and C2 reacted to the solar wind, forming wavy, changing structures. Astronomers compared it to a banner of light responding to every gust of plasma from the sun. This magnetic interaction indirectly revealed details about the solar field and the electrical properties of the gas expelled by the comet. As the days passed, the data confirmed something fascinating. 3I Atlas was not only an interstellar traveler but also a natural laboratory. Its trajectory allowed for the study of how matter from another stellar system responds to our star's environment. In every gas emission, in every change in brightness, information was hidden about its original composition, about the chemical processes that occur in distant worlds. The 29th of October arrived. From different points on the planet, observatories awaited the moment of perihelion. The James Webb pointed its instruments towards the region where the comet was hidden behind the solar glare, while Hubble prepared observations in ultraviolet wavelengths to detect possible fragments. The tension was evident. Any variation could be a sign of an internal energy release. When the data began to arrive, the monitors showed a sudden increase in total brightness. 3I Atlas reflected more light than expected and showed an accelerated expansion of its coma. Preliminary analyses indicated that the surface of the nucleus had partially fractured, letting escape jets of gas and dust in different directions. One of them, according to measurements, pointed directly towards the sun. The phenomenon lasted only a few hours, but it was enough to surprise everyone. No model had anticipated such a rapid response. The spectra obtained during that period revealed lines of intense ionization, a sign that the ejected material was interacting directly with the solar wind. It was the first time an interstellar object showed this level of activity within the solar system. After the perihelion, 3I Atlas began to move slowly outward, its curved trajectory moving away from the star that had just ignited it. However, the echo of its passage continued to resonate. The data captured in that moment would be analyzed for years, because every fragment of the spectrum, every variation in brightness, could reveal a detail about the materials that form other worlds. In the scientific community, a phrase was repeated that summarized the general feeling: "We have never seen a comet like this." And they were right. 3I Atlas, the traveler from interstellar space, had just written a new chapter in the history of astronomy. No one in the scientific community anticipated the way 3I Atlas would respond to solar heat. In early October 2025, when it was still beyond Earth's orbit, its brightness increased sharply for no apparent reason. Astronomers were accustomed to comets becoming more active as they approached the sun, but the speed with which this object did so was baffling. In just 5 days, its apparent magnitude changed by almost 1 unit, which equated to an increase of more than double in total luminosity. The event was reported simultaneously by observatories in Chile, Hawaii, and the Canary Islands and soon became the dominant topic in astronomical forums worldwide. The brightness increase did not seem to follow the empirical laws of cometary activity. Normally, the production of gas and dust grows following a predictable relationship with the distance to the sun. In contrast, 3I Atlas showed irregular jumps, as if its surface was reacting to internal impulses. Researchers from the Lowell Observatory compared the light curves and found that the rate of change was 8 times higher than that of an average comet under similar conditions. Something inside or on the nucleus was releasing energy in a sudden manner? The James Webb team pointed its NIRSpec instruments at the object to analyze the infrared emissions. What they found left the specialists speechless. The lines of CO2 and carbon monoxide were extremely intense, much more than corresponded to its distance. In contrast, the signals of water vapor were almost non-existent. This meant that water ice, a habitual component of comets, was not the main responsible for the activity. The brightness came from more volatile gases, capable of sublimating at much lower temperatures, which explained why the comet was activating so far from the sun. The finding was confirmed by optical spectra obtained from the Gran Telescopio Canarias. There, peaks were detected in the cyanogen band, a molecule that emits green light when excited by ultraviolet radiation. That was the cause of the emerald hue the images began to show. The comet seemed wrapped in a cloud of greenish light that intensified with each day. Astronomers described it as a ghostly glow, a visible manifestation of the exotic material composing it. Meanwhile, the La Silla Observatory in Chile measured its rotation using small periodic variations in brightness. The scientists calculated that the nucleus rotated once every 12 hours, a moderate pace but sufficient to produce internal tensions. If the surface was covered by a hardened crust and the interior contained trapped gases, this movement could provoke fractures and sudden eruptions. In other words, 3I Atlas was a pressurized comet, a body sealed for eons that, upon facing solar radiation, was releasing its content explosively. Photographic records from amateur observatories began to show an intriguing detail. The comet's tail, instead of pointing directly away from the sun, curved slightly to one side, forming an unusual angle. This deviation suggested the presence of a non-thermal component in the material ejection, perhaps a jet directed by the rotation. The phenomenon resembled active short-period comets, but the magnitude of the effect was much greater. Each turn of the nucleus changed the direction of the jet, creating a wavy pattern visible in long exposures. The scientific community then decided to concentrate resources to observe it continuously. A global monitoring campaign was created, including telescopes on 3 continents. The combined data revealed that the brightness variability followed a cycle of approximately 12 hours, coinciding with the nucleus's rotation. At each brightness maximum, the spectrum showed a temporary increase in the CO2 lines, as if the comet was breathing gas every time an active zone faced the sun. It was the first direct evidence of a periodic source of activity in an interstellar object. At the ESA's Planetary Studies Center, analysts attempted to model the phenomenon. They used thermodynamic simulations based on the conductivity of ice and the expansion of gases trapped under a porous crust. The results indicated that small bubbles of CO2 could accumulate pressure until fracturing the surface, expelling material at speeds over 150 meters per second. Each eruption released thousands of tons of gas and dust, enough to increase the brightness of the entire comet. These micro-explosions explain the observed peaks and also the peculiar jet directed towards the sun. By mid-October, space telescopes registered a second, even more intense event. The James Webb captured a sudden infrared flash that lasted less than 6 hours, accompanied by an increase in visual luminosity. The amount of energy released was equivalent to the evaporation of about 10 million kilograms of CO2 ice. It was not an explosion in the violent sense, but a sudden release of gas confined to the surface. The phenomenon was informally dubbed the Atlas Pulse. Since then, every variation in brightness was compared to that reference event. Scientists highlighted the importance of these pulses for understanding comets from other systems. If 3I Atlas formed in an environment with an abundance of solid carbon dioxide, that means its star of origin could have had an extremely cold external region. The study of its molecular proportions therefore served as a window into the climate of another solar system. Analyzing its gases was, in a way, analyzing the chemistry of an unknown world. The brightness increase also brought a technical challenge. The coma became so extensive that traditional photometric models ceased to be accurate. Astronomers had to use specialized filters to separate the light of the nucleus from that of the surrounding dust. Hubble images revealed that the coma extended over 80,000 kilometers, double what was predicted. At the center, the nucleus remained unresolved, a bright point surrounded by layers of gas changing density every hour. Meanwhile, researchers from the solar orbiter measured how the solar wind affected the comet's tail. During the brightness peaks, the sun's magnetic field deformed slightly in that region, a minuscule but detectable effect. It was the first time a solar instrument registered the wind's response to an interstellar comet. This data allowed for the calculation of the exact amount of charged particles the comet emitted during its outbursts. On the 20th of October, terrestrial observatories confirmed that the brightness of 3I Atlas had stabilized at magnitude 8, but with short variations every 12 hours. Astronomers knew the true challenge would arrive when it reached perihelion, because there the radiation would be 10 times more intense. If the comet had already shown such activity at 1.6 astronomical units, no one could predict what would happen at 1.4. That uncertainty turned 3I Atlas into the most observed object of 2025. NASA organized live observation sessions from the Space Telescope Science Institute's platform, and ESA published maps of its trajectory updated every hour. Public interest grew. For the first time, millions of people followed in real time the passage of an interstellar visitor confronting the sun. Scientists, however, remained cautious. They knew that extreme luminosity could be a prelude to fragmentation, although there were no signs of rupture. Until that moment, high-resolution images showed an intact nucleus. Everything indicated that 3I Atlas was resisting, though at the cost of releasing enormous amounts of gases. The exact nature of its surface remained a mystery, but its overflowing brightness had become an invaluable tool to study it in greater detail. When the object crossed the 1.45 astronomical unit line, the James Webb registered one last sequence of spectra before losing it to the solar glare. Those observations would be analyzed for months. Among them was hidden the key to the unexpected behavior of 3I Atlas. the direct evidence of how interstellar matter reacts to the energy of a star. The unexpected brightness not only transformed the perception of the comet, it also changed the way astronomers understand cometary activity. It showed that even at great distances, exotic bodies can release energy in unpredictable ways. For many, it was the demonstration that the universe still holds mechanisms we are only beginning to discover. The 29th of October 2025 marked the critical point of the journey of 3I Atlas, the perihelion, the instant the interstellar visitor reached the minimum distance to the Sun. 4 days, telescopes had followed its approach with extreme precision. But it was in those hours that the phenomenon that surprised the entire astronomical community became evident. At 14:23 UTC, the instruments of the solar orbiter registered a sudden increase in particles in the direction of the Sun. Shortly after, terrestrial observatories confirmed that the comet had released an enormous amount of gaseous material and dust, forming a bright plume oriented directly towards the star. Unlike comets from the solar system, whose tails always point away from the Sun due to the pressure of the solar wind, 3I Atlas showed contrary behavior. Its main jet seemed to be directed towards the very source of the radiation. Scientists reviewed the data again and again, sure it must be an optical illusion caused by perspective, but orbital calculations and the jet vectors confirmed the impossible. The ejection was real and was oriented almost in line with the Sun. The phenomenon was detected simultaneously by the Stereo A telescope and by Hubble, which captured images showing a thin column of material extending towards the inner solar system. The spectra revealed that the jet was composed mainly of carbon dioxide and fragments of dust-rich in amorphous carbon. There were no signs of water ice. This was unprecedented. It meant that solar heat had penetrated sufficiently to sublimate the most volatile compounds without destroying the nucleus. 3I Atlas was responding to the Sun in a way that traditional models could not reproduce. NASA researchers compared the sequence with historical records of comets like Lovejoy or Ison, which had passed close to the Sun in previous decades. However, none showed a jet directed towards the star with that intensity. The phenomenon quickly received an informal name within the scientific community: the anti-tail active, in reference to the direction opposite to the expected one. But this case was not simply an illusion caused by observation geometry. The velocity vectors of the particles coincided with a real flow in the solar direction. The James Webb, observing from its position at Lagrange point 2, just managed to capture the last infrared traces before the Sun's glare saturated it. Even so, the data were sufficient to estimate the temperature of the expelled material, around 230 Kelvin, significantly colder than the comet's surface. This suggested that the gas was expanding rapidly from an internal cavity, a sort of cosmic breath releasing its contents into space. Meanwhile, the solar orbiter registered a temporary increase in the density of the solar wind in that region, accompanied by a slight magnetic disturbance. Some interpreted this as evidence that the comet's material had interacted directly with the solar plasma. It was an extraordinary situation. For the first time, an object from another stellar system was altering, albeit minimally, the immediate environment of the Sun. In analysis laboratories, astrophysicists attempted to reconstruct the physical process behind that ejection. The most accepted hypothesis pointed to a phenomenon of internal overpressure. For millions of years, the comet had traveled in the absolute cold of interstellar space, accumulating gases in pores and cracks beneath a hardened layer. When finally the Sun's heat reached those pockets, the expansion of CO2 and carbon monoxide broke the surface like a valve releasing vapor. The result was a sudden and directional ejection, enhanced by the nucleus's rotation. The La Palma Observatory registered brightness variations that coincided with the moment of the outburst. The comet's apparent magnitude increased by almost 1 point in just 3 hours. The images showed a much denser coma and a filamentary structure in the jet zone, with particles extending over more than 50,000 kilometers away. The flow appeared so stable that astronomers compared it to a geyser of ice and gas expelled into the vacuum. The event was not only a visual spectacle but also a source of invaluable scientific information. The released particles reflected the deep composition of the comet, never before exposed to the vacuum. The spectra showed traces of complex organic compounds, including formaldehyde and hydrogen cyanide, molecules essential for prebiotic chemistry. Their detection was consistent with what had been observed in other comets, but their proportion was different, indicating a different chemical history. These signals confirmed that 3I Atlas came from a stellar environment where the formation of organic molecules occurred under conditions of extreme cold and radiation. Scientists from ESA published a preliminary report detailing the characteristics of the event. They estimated that the total ejected mass was equivalent to more than 40 million kilograms over a period of less than 1 day. Although this quantity represented an infinitesimal fraction of the comet's total, it was enough to modify its appearance and produce the spectacular column observed from Earth. The dynamics of the jet, according to calculations, would have slightly altered its rotation, accelerating it by 3%. The interaction with the solar wind generated an additional luminous effect. As the sun's charged particles struck the expelled gas, ionization discharges occurred, making the plume glow in ultraviolet wavelengths. From a physical standpoint, it was a dance between two completely different systems, an interstellar body and the extended atmosphere of our star. For scientists at the Institute of Astrophysics of Andalusia, that encounter offered an unrepeatable opportunity to study the boundary between cometary dust and solar plasma. While the comet passed behind the sun from Earth's perspective, visual observations stopped for a few days. However, the instruments of the solar orbiter and the stereo satellite continued detecting the cloud of material moving towards the solar corona. Part of this matter was absorbed by the wind, but another fraction dispersed into a wake that remained floating in the inner space. Models showed that this band of particles would remain for weeks traveling near Mercury's orbit before fading away. When 3I Atlas reappeared on the opposite side of the Sun in early November, telescopes confirmed it had survived the perihelion. Its nucleus remained intact, though it showed a more irregular shape and an extended tail of over 100,000 kilometers. The brightness had diminished, but the record of the event was already sufficient to rewrite part of the knowledge about interstellar comets. What most caught the astronomers' attention was the resilience of the nucleus. Despite the extreme thermal stresses, it did not disintegrate or fragment, suggesting a more compact structure than expected, perhaps cemented by metallic materials or solid silicates. Analyses by Hubble and Webb in the following days confirmed that the nucleus maintained a higher density than that of common comets. This coincided with the observations of its trajectory. There were no signs of significant mass loss. Its behavior had been violent, yes, but controlled. 3I Atlas seemed to have released internal pressure without compromising its structural stability. In scientific circles, the event was described as a natural experiment in extreme physics. No terrestrial laboratory could reproduce the conditions of that encounter between interstellar matter and solar energy. The data collected during the outburst would be enough to fuel years of research on the thermodynamics of comets. For the first time, scientists had direct evidence of how a body formed under another star responded to the sun of our galaxy. That ejection towards the sun was the clearest proof that 3I Atlas did not behave like a conventional comet. Its composition, its structure, and its way of releasing energy revealed a new type of object, a messenger from deep space that allowed us to observe for a few moments the interaction between two worlds separated by unimaginable distances. When 3I Atlas began to show the jet of gas oriented towards the sun, the James Webb Space Telescope was in a privileged position to observe it from its equilibrium point at Lagrange point 2. From that distance, 1.5 million kilometers behind Earth, Webb had the advantage of seeing the comet without the sun's direct glare, and its infrared instruments could analyze the chemical composition with unprecedented detail. It was the first time an object from another stellar system would be examined with this technology. The NASA and ESA teams activated the critical time observation mode reserved for non-repeatable events. The spectrometers, NIRSpec and MIRI, captured the comet's thermal radiation during the phase of maximum activity. The initial data revealed a spectrum dominated by bands of carbon dioxide, carbon monoxide, and simple organic molecules like methane and hydrogen cyanide. The almost total absence of water was the first big surprise. 3I Atlas was not a typical Oort cloud comet, but an object formed in a region where water ice could never have existed in quantity. The spectrum also showed an unusual absorption pattern at wavelengths near 3 microns, an indication of a surface covered by complex carbonaceous materials. The team compared these signals with those of other comets observed by Webb, like Hartley 2 and Tempel 1, and discovered that the signatures of 3I Atlas coincided more with the residues of young protoplanetary disks than with mature comets from the solar system. In other words, 3I Atlas seemed to have originated in a newly born star-forming region, where the material had not yet undergone differentiation processes. From the thermal data, scientists calculated the surface temperature of the nucleus, around 170 Kelvin. That figure was surprisingly low, considering the intensity of the solar radiation it was receiving. It meant that the outer layer of the comet acted as a very efficient insulator, capable of keeping the interior frozen while releasing gases through localized fractures. Thermodynamic models suggested that this crust had a thickness of between 10 and 20 centimeters, hardened by 1 billion years of exposure to cosmic rays outside our system. Mid-infrared images showed an asymmetric glow that coincided with the position of the jet towards the Sun. The energy emitted in that region was 3 times higher than that of the rest of the surface, confirming localized activity. Webb also detected solid particles a few microns in diameter, probably silicate grains expelled with the gas. This mixture of organic and mineral materials suggested that the comet contained remnants from both the rocky interior and the icy zones of its system of origin. One of the most valuable results was the detection of an anomalous proportion of carbon and oxygen isotopes. Webb registered a 13C to 12C ratio higher than expected, something only observed in galactic regions where star formation has been intense over long periods. This allowed researchers to place the possible origin of 3I Atlas in an older zone of the Milky Way, perhaps some 300 light-years from the Sagittarius arm. It was the first time an interstellar object brought with it an isotopic record that could be used to trace its provenance. Webb followed the comet for 4 consecutive days. As 3I Atlas began to move away from the Sun, its infrared emission slowly decreased, but the spectral patterns remained stable. There were no signs of fragmentation or catastrophic mass loss. The activity seemed controlled, as if the nucleus was releasing pressure periodically. This stability contrasted with the explosive behavior of solar comets like Ison, which disintegrated during its first encounter with the heat. 3I Atlas, in contrast, resisted. It was a clear message. Its structure was much more resistant than imagined, perhaps cemented by metals or refractory compounds. Specialists from the Max Planck Institute for Astronomy analyzed the temperature distribution over the nucleus and found a difference of up to 40 Kelvin between hemispheres. This thermal inequality generated tensions that explained the directional gas leaks. They also deduced that the comet's rotation had accelerated slightly after perihelion, a product of the angular momentum transmitted by the ejection. Each jet functioned as a natural thruster altering its spin. Webb did not work alone. Hubble, operating in ultraviolet wavelengths, observed the molecules excited by solar radiation. The comparison of both datasets allowed for the construction of a 3-dimensional model of the gas behavior around the nucleus. The simulators showed that the material was expelled in pulses, each lasting a few hours before subsiding. This rhythm coincided with the comet's rotation, confirming that the active zones turned on and off periodically. In the laboratories of NASA's Goddard Center, the Webb spectra were translated into molecular density graphs. There, more than 20 distinct compounds were identified: ammonia, formaldehyde, ethane, ethylene, and even traces of acetylene. Some of them had never been detected in interstellar comets. The pattern resembled more the chemistry of protoplanetary disks observed around other young stars. This meant that the matter that formed 3I Atlas had emerged at a very early stage of its system, before the planets had finished consolidating. Follow-up images taken by the MIRI instrument after perihelion revealed something even more intriguing: a series of helical structures in the comet's tail. These spirals seemed to form from the combined rotation with the periodic release of gas. The effect, though difficult to visualize, served to precisely measure the rotation speed and the frequency of the pulses. Never before had such a defined pattern been observed in an interstellar object. The results obtained by the James Webb were published in a Nature Astronomy preprint a few weeks later. The document stated that 3I Atlas represented a new type of interstellar comet, chemically distinct and structurally resilient. That phrase synthesized the impact of the discovery. Until that moment, astronomers believed comets were fragile conglomerates of ice and dust. Now they knew that at least some formed under other stars could withstand extreme conditions without breaking. Furthermore, the Webb data helped improve planet formation models. The observed isotopic ratios indicated that the material of 3I Atlas had condensed in an environment rich in ultraviolet radiation, probably near a star more massive than the Sun. This implied that the chemistry of planetary systems can vary drastically depending on the type of star, a conclusion that extends the known diversity of possible worlds. During the last days of tracking, Webb detected a slight decrease in the CO2 emission, a sign that the comet was entering a quieter phase as it moved away. However, scientists estimated it would remain active for at least several more months, while its surface released the accumulated heat. These periods of respite would serve to study how the remnant gases affect the tail and the dispersion of dust in the inner space. The James Webb, with its ability to detect wavelengths invisible to the human eye, gave us a complete picture of the comet, its structure, its composition, and its resilience. But it also reminded us of something deeper, that the universe is not a static place, but a stage of constant exchange between worlds that have never known each other. 3I Atlas was the living proof of that cosmic dialogue, an open door to the matter of other stars that for a few moments came close enough to tell us its story. The first images sent by the James Webb, Hubble, and the solar orbiter provoked an immediate reaction in the control centers of the major space agencies. NASA and ESA knew that the behavior of 3I Atlas represented an unprecedented phenomenon and, above all, a scientific opportunity that could not be repeated. Within hours, both organizations coordinated an international network of observatories to monitor every change in the object's brightness, trajectory, and composition. The response was rapid but also prudent. Public communications underlined the need to analyze the data before drawing hasty conclusions. At the Jet Propulsion Laboratory in California, specialists in orbital dynamics reviewed the comet's updated parameters. They confirmed that despite the ejection of material towards the Sun, the trajectory had not deviated significantly. 3I Atlas followed a hyperbolic curve that would lead it out of the solar system in the following months. Its passage represented no risk for Earth or the inner planets. This detail became an essential part of the official bulletins. They wanted to avoid the wave of disinformation that usually accompanies every major astronomical discovery. NASA published on the 31st of October a preliminary report titled, Interstellar Visitor 3I Atlas Nears Perihelion, Observed Activity Unprecedented. The document accurately described the data from Webb, Hubble, and terrestrial observatories, confirming the interstellar nature of the object and its extraordinary resistance to solar heat. The agency highlighted 3 points: the unexpected increase in brightness, the composition rich in carbon dioxide and carbon monoxide, and the absence of water in the spectrum. These results, they said, suggest a formation process in an extremely cold environment, possibly at the edge of a planetary system different from our own. Meanwhile, in Darmstadt, Germany, the ESA Space Operations Center brought together the teams from the Solar Orbiter and the Gaia Observatory. Their goal was to compare the exact position of 3I Atlas with models of the solar magnetic field. The stereo data showed a small perturbation in the solar wind coinciding with the comet's ejection. It was a faint signal, but enough to ignite the curiosity of solar physicists. If that interaction was real, it meant that a portion of the comet's material had penetrated the inner heliosphere, mixing temporarily with the Sun's plasma. On the 2nd of November, ESA issued a joint statement with NASA, describing 3I Atlas as a window into the chemical origins of other stellar systems. The note detailed that the two organizations would share their data in an open-access database for researchers worldwide. It was not a minor gesture. Rarely had the global scientific community collaborated with such speed. Astronomers knew that every hour of observation counted because the comet would soon be lost behind the Sun. In Houston, the Johnson Space Center opened a temporary room dedicated exclusively to the analysis of 3I Atlas. Scientists compared the detected molecular proportions with those of meteorites and dust samples collected by the Stardust and Rosetta missions. The result was intriguing. The carbon and oxygen ratios partially matched those of a rare type of carbonaceous chondrite, reinforcing the idea of an origin in an outer region of a planetary system. However, the heavier isotopes did not fit any previous record. This meant the comet came from a zone of the galaxy where the stellar composition was different, a detail that excited astrophysicists specializing in interstellar composition. The James Webb continued providing data while the teams on the ground processed the spectra. NASA decided to release part of the observations on its public portal, and the images quickly went viral. They showed a bright head surrounded by a greenish-blue coma and a double tail extending over 100,000 kilometers. Although the phenomenon was purely natural, popular interest reached levels comparable to those of major planetary missions. The agency took advantage of the attention to launch educational campaigns, explaining the difference between scientific observation and speculation. In Europe, ESA organized a special conference from its center in Noordwijk, Netherlands. There, the Spanish astrophysicist Javier Martínez Santos presented the first results from the Solar Orbiter, a series of variations in the density of the solar wind attributable to the passage of 3I Atlas's plume. His presentation concluded with a phrase that resonated with the attendees. For the first time, we have seen how matter from another stellar system interacts directly with the solar environment. The news traveled through specialized media within hours. Scientific interest then transformed into a race to record every detail before the comet disappeared. The Institute of Astrophysics of the Canary Islands, the Paranal Observatory, and the Gran Telescopio de Hawaii coordinated a continuous schedule of observations. On the following nights, the instruments measured minimal variations in the nucleus's rotation, confirming that the gas ejection had acted as a natural thruster. ESA planned to include this data in its comet dynamics models for future missions like Comet Interceptor, whose launch is planned for 2029. As more results were published, the scientific community showed a mixture of caution and astonishment. Some specialists compared the resilience of 3I Atlas to that of metallic bodies, while others insisted that the observed density could be explained by a gradual compression of the material over millions of years. NASA and ESA maintained their conservative stance. This was not an artificial object or an anomalous phenomenon, but a natural body offering unprecedented clues about primordial matter. This clarity was necessary to counter unscientific theories beginning to circulate on social networks. The official communications also highlighted the educational importance of the event. NASA organized live streams with astronomers answering public questions, explaining how a spectrum is interpreted or why the tail's orientation could seem confusing. ESA, for its part, created three-dimensional visualizations of the comet's path and shared them freely with schools and universities. The goal was to turn general curiosity into learning, a way to leverage media interest for science outreach. Internally, the engineers of Webb and Hubble began to discuss how to adapt observation protocols for future interstellar objects. The success of 3I Atlas demonstrated that existing platforms could react quickly if coordinated properly. This cooperation between agencies became a model of international scientific collaboration. On the 8th of November, NASA and ESA published a more detailed joint report. In it, they stated that 3I Atlas had provided direct evidence of the presence of complex organic compounds in interstellar matter and that its thermal behavior indicated a cohesive nucleus, not a loose dust structure. The document was reviewed by multiple institutions, and its main conclusion was clear. Interstellar comets are not simple wandering fragments, but messengers from other solar systems that can survive the passage by the Sun. That same day, the director of NASA's Science Mission Directorate, Nicola Fox, gave an interview in which he summarized the meaning of the discovery. Every time we observe an interstellar object, we have the possibility to touch, even if indirectly, the materials with which other suns built their planets. 3I Atlas is a window into the chemical history of the galaxy. In the analysis laboratories, researchers began preparing more extensive scientific publications. The processing of the Webb data required weeks of calibration, but the first conclusions already outlined a fascinating panorama. An interstellar object that resisted the sun's radiation bath, releasing organic compounds and exotic gases without fragmenting. The agencies planned to continue observations as the comet moved away, taking every opportunity to study how it cools and how its activity dissipates. At that point, international cooperation reached a level few would have imagined. NASA, ESA, the Japanese Space Agency, and the European Southern Observatory were working under a single tracking schedule. The goal was no longer just to understand 3I Atlas, but to lay the groundwork for future missions that will intercept interstellar objects in transit. The message was clear: exploration will not stop at the boundaries of the solar system. While world headlines spoke of the comet that defied the sun, in the corridors of the agencies, an expectant silence reigned. Scientists knew the work was just beginning. Every bit of information stored in the memories of Webb, the solar orbiter, and terrestrial observatories would be meticulously analyzed for years. And in the midst of this global effort, one idea was repeated among the researchers: that 3I Atlas had not only crossed the solar system, but also the frontiers of human knowledge. After the perihelion, when 3I Atlas began to slowly move away from the sun, astronomers concentrated on understanding how it had withstood such an extreme encounter. The observations from the James Webb, Hubble, and terrestrial telescopes revealed something that baffled even specialists in cometary physics. The nucleus showed no signs of fragmentation or significant mass loss. The surface seemed to have changed, yes, but the body remained intact. Understanding how an interstellar object managed to survive such high temperatures became a scientific priority. The analysis of the thermal data collected during the approach showed that the nucleus's temperature had not exceeded 200 Kelvin. In theory, at that distance from the sun, the surface of a conventional comet should have reached at least 250 or 260 Kelvin, enough to cause its partial disintegration. However, 3I Atlas maintained a surprising thermal equilibrium. The secret, according to models developed by the Institute of Astrophysics in Paris, resided in the nature of its outer crust. That layer, hardened over millions of years of exposure to interstellar space, acted as an insulating shield that delayed the conduction of heat towards the interior. Astronomers compared its behavior with that of solar system comets that have passed near the Sun, like Ison or Lovejoy, and noticed a crucial difference. While those comets show temperature peaks that melt their surface within hours, 3I Atlas released gas in a gradual and directed manner. This indicated that its nucleus was composed of materials with different sublimation points. First the most volatile, like carbon dioxide, and then the less sensitive ones, like carbon monoxide and methane. This staged release allowed the comet to regulate its mass loss without collapsing. In the energy density graphs prepared from the Webb data, zones of pronounced thermal contrast were observed. Regions reaching 190 Kelvin alongside others that barely surpassed 150. This temperature difference generated internal tensions and was precisely what explained the periodic gas jets detected before perihelion. The heat, by not distributing uniformly, created pockets of pressure under the surface. When the comet's rotation exposed a crack to the Sun, the accumulated pressure burst out in the form of a luminous jet. Researchers at the Max Planck Institute conducted simulations with thermal fracture models and discovered that the surface material must be a mixture of fine silicates, amorphous carbon and metallic traces. All of them good electrical conductors but poor thermal conductors. This explained the apparent paradox of a body that heated up on the outside and remained cold on the inside. The microfractures observed after perihelion confirmed the uneven expansion of this hardened layer. But the most surprising thing was that these fissures did not grow or transform into larger cracks. The comet seemed to possess a cohesive structure, perhaps cemented by metallic compounds or by ice mixed with minerals. At the Goddard Space Flight Center, a group of physicists modeled the comet's response to the solar radiation flux. Using data from the solar orbiter, they calculated the exact amount of energy the nucleus absorbed during the hours of perihelion. The result was lower than expected. The surface reflected almost 70% of the incident light, a reflectance comparable to that of metallic asteroids. This explained why the nucleus did not melt. 3I Atlas had a bright surface that returned a large part of the solar energy to space. The coincidence with the albedo measurements taken by Webb confirmed this unique characteristic. As the comet moved away, the surface temperature began to drop rapidly. The sensors detected a cooling of almost 60 Kelvin in just 5 days. The gases that were still evaporating in the coma froze again, forming a thin layer of frost over the nucleus. This recondensation phase was observed by Hubble, which detected a decrease in brightness and a more compact concentration of the coma. The comet, in a way, was closing the wounds opened during its encounter with the Sun. The thermal behavior of 3I Atlas also gave clues about its possible internal density. Gravitational models estimated that the nucleus had an average density close to 1.5 grams per cubic centimeter, significantly higher than that of solar system comets, which rarely exceed 0.6. This difference reinforced the hypothesis of a compact structure with fewer pores and fewer internal voids. In other words, it was a dense comet, almost rocky, more similar to an icy asteroid than to a fragile conglomerate of dust and ice. In Europe, specialists at the Nice Observatory compared the data on albedo, density, and composition, concluding that the nucleus of 3I Atlas could be formed by a heterogeneous mixture of silicates and exotic ices. The proportions of methane and CO2 suggested a formation environment at temperatures below 24 Kelvin, probably beyond the snow line of its home system. Such conditions are only found in the outer regions of protoplanetary disks, which meant the comet came from the confines of a distant system, perhaps ejected by the gravitational interaction of giant planets. The thermal analysis also helped understand the orientation of the jet towards the Sun. When the internal pockets of gas expanded, the pressure was not released radially, but followed the most recent cracks opened by thermal contraction and expansion. Some of these fractures were oriented towards the illuminated face, so the resulting ejection pointed in the solar direction. It was a natural phenomenon, a direct consequence of its asymmetric structure. In the spectroscopy laboratories of the Marshall Space Center, researchers examined the signals emitted by the detached material. They discovered that the expelled dust contained traces of iron, magnesium, and nickel. The presence of heavy metals in detectable concentrations reinforced the idea of a partially rocky nucleus. Those elements, oxidizing under solar radiation, produced a faint reddish glow at the base of the coma, visible in high-exposure images. It was a subtle detail, but crucial for understanding the object's composition. The comet's thermal behavior, beyond its resilience, raised new questions about the evolution of interstellar bodies. Could other objects of this type contain materials so dense and compact? How many survived the passage by stars before being lost in the void? For scientists, 3I Atlas represented an example of equilibrium between destruction and survival, a testimony to how matter can adapt to radically different environments. During the following weeks, telescopes measured a gradual decrease in activity. The tail lengthened, but its density reduced. The jets were no longer as vigorous, and the overall brightness dropped by almost 1 magnitude. The comet, however, remained visible to large aperture observatories, offering the last flashes of its internal energy. On Webb, the instruments registered a series of weak peaks in the infrared spectrum, a product of the cooling residual gas. These flashes were the last thermal sighs of the interstellar traveler, evidence that heat was still trapped beneath the surface. In time, that heat would dissipate completely, and 3I Atlas would return to the absolute cold that had accompanied it for millennia. The resilience of the nucleus, its thermal insulation, and the partial metallic composition transformed the view astronomers had of comets from other systems. Until then, it was believed they were all fragile conglomerates. 3I Atlas demonstrated that some can be solid structures capable of withstanding the most hostile environments. In that sense, the comet not only survived the sun but also survived human expectations. When the last data from the James Webb were transmitted to Earth, a sense of closure ran through the research centers. The comet's thermal history was complete, from its freezing in a distant corner of the galaxy to its awakening in front of our star and its return to the silence of space. But the obtained information would remain alive. In every bit of analyzed radiation lay the imprint of an alien world, a testimony of the extreme heat and cold that defined the life of the universe. On the 3rd of November 2025, when 3I Atlas was already leaving its closest point to the Sun, a sudden event caught the attention of all observation centers. Telescopes in Hawaii and Chile detected an abrupt variation in brightness, an increase of almost 1.5 magnitudes in less than 2 hours. It was not a simple thermal oscillation nor an instrumental fluctuation. It was a real outburst, a new episode of activity that nobody expected after the perihelion. Scientists immediately called it the second pulse, though they would soon understand it was something different, something much more powerful than the previous gaseous pulses. The first images showed a rapid expansion of the coma, accompanied by a secondary cloud of dust extending in the direction opposite to the main tail. The comet's structure seemed intact, but the glow reached its maximum within minutes. Observatories in the southern hemisphere, including Paranal and La Silla, managed to capture the complete sequence. Those photographs showed a kind of halo surrounding the nucleus, as if a layer of its surface had suddenly detached. The spectral emissions of carbon dioxide increased by 40%, confirming a massive release of gas. The event was surprising for its timing. The comet was already moving away from the Sun, so its activity should have diminished. Researchers from the Planetary Science Institute in Arizona proposed a provisional explanation. According to their models, the thermal stresses accumulated during the perihelion would have generated internal fractures that took days to propagate. When these cracks reached deep pockets of gas, the released pressure caused a delayed eruption. It was an echo of the encounter with the Sun, a sort of last breath from the comet. The James Webb, which still maintained observation in automatic mode, detected the change almost immediately. Its infrared sensors registered a sudden increase in the radiation from hot dust, with peaks at 10 and 12 microns. Preliminary analyses indicated that the local temperature of the coma rose to 300 Kelvin, much higher than during perihelion. Webb transmitted the data in real time to the Goddard Center, where scientists confirmed that something had altered the comet's thermal structure. It was as if an entire portion of its surface had collapsed into the vacuum, releasing gas and dust in a brief but intense burst. At the same time, the solar orbiter detected a minor perturbation in the solar wind with an elevated particle density coming from the comet's direction. This meant the ejection had been powerful enough to affect the immediate interplanetary space environment. In short, 3I Atlas had launched a cloud of material visible from millions of kilometers away, a final act of energy that defied predictions. During the following hours, telescopes in the northern hemisphere began to record the evolution of the phenomenon. Unlike previous outbursts, this one did not disappear quickly. The dust cloud remained visible for days, expanding as the comet continued on its way. Particle dynamics models developed by the University of Cambridge showed that the expansion velocity exceeded 250 meters per second. That rate could only be explained by a partial structural collapse of the surface material. However, the main nucleus did not break. Hubble observations confirmed it remained a single body, though slightly more irregular. The comet's brightness began to decrease again, but the secondary cloud persisted, leaving behind a luminous trail that remained visible for more than a week. In astronomical forums, observers compared the event to a mini-controlled explosion, a phenomenon demonstrating the comet's capacity to release energy in a contained manner. NASA's and ESA's interest was immediately reactivated. Multidisciplinary teams analyzed the data sequence from Webb, Hubble, and terrestrial observatories to reconstruct the moment of the outburst. The most striking result came from the ultraviolet spectrum. For the first time, clear signals of complex organic compounds fragmenting in space were detected. The characteristic bands of formaldehyde and hydrogen cyanide showed an abrupt decline, a sign that the molecules had been destroyed by the released energy. This meant the outburst was not only physical but also chemical. Subsequent analysis revealed another fascinating detail. In the minutes following the event, the comet emitted a glow on its night side more intense than usual, visible even in optical cameras. This light came from the ionization of diatomic carbon in the coma, activated by solar rays interacting with the newly released gas. In simple terms, the comet had ignited its own aurora, a plasma display visible across the vacuum. The phenomenon sparked comparisons with the behavior of geysers on Saturn's moon Enceladus. As there, the accumulated heat was released through a process of internal pressure that opened subterranean channels. However, in 3I Atlas the scales were much larger. The total estimated energy of the outburst was equivalent to the detonation of 300 tons of TNT released without causing global destruction. This balance between power and stability again perplexed scientists. How could such a small body regulate its energy so precisely? At ESA, specialists in cometary dynamics suggested that the nucleus's rotation played a fundamental role. During perihelion, the comet had accelerated its spin, and this additional rotation may have redistributed the internal stress. When the pressure exceeded the cohesion limit at a specific point, the surface gave way, releasing gas outward. It was a logical explanation, but it did not eliminate the general surprise: an interstellar comet demonstrating a resilience no previous model had contemplated. The unexpected event also allowed for the analysis of the immediate response of the space environment. Satellites monitoring solar radiation detected a small alteration in the density of interplanetary dust, enough for some scientists to speculate that microscopic fragments of the comet could cross the orbit of Mars weeks later. Although these particles were tiny and posed no danger, their detection offered a unique opportunity to track interstellar material within our system. Meanwhile, on Earth, the most powerful observatories continued recording the evolution of the cloud. Spectra from the Very Large Telescope showed the formation of a double structure: an inner coma still fed by residual gas and an outer one composed of inert dust reflecting sunlight. This contrast helped researchers determine the amount of material expelled: more than 50 million kilograms in less than 1 hour. Over the following days, the comet's total brightness returned to its previous level. The secondary cloud dispersed, and the environment regained its normal appearance. However, the scientific impact of the event was immediate. Specialized journals began preparing articles on the post-perihelion superactivity of 3I Atlas, a phenomenon that called into question conventional thermal models. For many researchers, this event demonstrated that cometary activity does not depend solely on proximity to the Sun, but also on the thermal memory of the material. The unexpected event, as it was officially recorded, became a turning point in the study of interstellar objects. For the first time, it was observed how a comet could experience a significant outburst without fragmenting, releasing organic matter and then returning to calm. It was a lesson in cosmic equilibrium, a showing that even in the apparent silence of space, self-regulation mechanisms exist. When the news became public, NASA issued a brief but forceful statement: 3I Atlas has demonstrated that the boundary between stability and destruction in comets is wider than we believed. In spectrometry laboratories, scientists continued decomposing the data, but all agreed on one thing: The universe had just shown a new facet of its complexity. And as the comet continued slowly moving away from the sun with its fading glow and intact structure, astronomers understood that this final outburst was not an accident, but a natural part of its adaptation, a response of matter to the heat of a star it had never known. The post-perihelion outburst left the scientific community in a state of silent awe. In the first minutes, the teams controlling the James Webb and Hubble thought a sensor failure had occurred. The light curves rose so sharply that some monitoring algorithms discarded the readings as errors. But when images from telescopes in Chile, Hawaii, and the Canary Islands confirmed the same pattern, the reality was undeniable. 3I Atlas had awoken again, releasing an immense amount of energy without destroying itself. At the Jet Propulsion Laboratory, the operations room filled with messages. Scientists from around the world exchanged data in real time. Cometary dynamics experts reviewed trajectory vectors. Astrophysicists compared brightness intensity with thermal models, and planetary chemists analyzed the spectral lines. The scene recalled the days of the Apollo missions. Lit screens, tense voices, and a mixture of excitement and bewilderment. No one expected an interstellar object could show so much activity after passing through the most dangerous point of its journey. The first hypotheses emerged within hours. Some researchers thought the outburst was due to an internal fracture caused by the temperature change between hemispheres. Others proposed that the comet contained reactive compounds like frozen peroxides that could have decomposed suddenly. However, no single explanation could justify the magnitude of the phenomenon nor its brief duration. A joint analysis was necessary. At the ESA headquarters in Darmstadt, the Solar Orbiter mission engineers convened an urgent meeting. The satellite's plasma sensors had detected a pulse of particles coinciding with the optical outburst, a tangible signal that the comet had interacted with the solar wind. It was the first time an interstellar object produced a measurable perturbation in the heliosphere. Solar physicists analyzed the record carefully and discovered that the pulse propagated like a small wave through the magnetic field. This confirmed the event had been real, not an optical illusion or an instrumental artifact. In parallel, the Planetary Science Institute in Tucson published a provisional report. In it, the researchers stated that the outburst of 3I Atlas could be considered the first documented case of delayed activity in an interstellar comet. According to their interpretation, the nucleus had accumulated heat in the inner layers during perihelion, and days later, that heat released gas trapped in regions that still remained sealed. The result was a deferred eruption, like a final exhalation. The term post-perihelion outburst began to circulate in scientific articles and became the official label to describe the event. The reactions were not limited to laboratories. On academic networks like ResearchGate and forums of the International Astronomical Union, discussions multiplied. Some veterans compared the surprise to that caused by Oumuamua in 2017, when its non-gravitational acceleration baffled the world. However, the case of 3I Atlas was different. Here there was no instrumental ambiguity, but a visible and verifiable physical phenomenon. The initial consensus was unanimous: the comet had just expanded the boundaries of what was believed possible. On the 5th of November, just 2 days after the event, NASA organized a press conference. Facing a room full of journalists, Nicola Fox and Thomas Zurbuchen, both executives of the science program, calmly explained the confirmed facts. "What we have seen is a natural process, but an extraordinarily powerful one," declared Fox. 3I Atlas has shown a form of activity we had not observed in any other interstellar body. There is nothing mysterious or artificial in its behavior, only a physics we are beginning to understand. That phrase set the tone for all subsequent media coverage. Awe, but without speculation. Theoretical astronomers then began a race against time to reproduce the event through simulations. At the University of Maryland, Michael Kelly's team used three-dimensional thermal transfer models to simulate the comet's interior. They introduced a highly refractory outer layer with low thermal conductivity and a more porous nucleus rich in frozen CO2. The result coincided almost exactly with the observations. After receiving an intense dose of radiation, the heat slowly penetrated until a cavity inside, accumulating pressure until it released all at once. The simulation showed a gas ejection directed towards the illuminated hemisphere, just like in the real images. The results were presented in a joint virtual seminar between NASA and ESA. Over 500 researchers connected to discuss the findings. One of the most debated points was the structural stability of the nucleus. If 3I Atlas could release so much energy without fragmenting, it meant its interior was much more resistant than anticipated. Some suggested the cohesion came from metallic bonds or mineral compounds acting as cement. Others pointed to the possibility that the comet had lost much of its original porosity during its interstellar travel, compacting over time. Meanwhile, observational astronomers continued collecting data. The Very Large Telescope recorded the evolution of the coma after the outburst. The analyses showed that although the gas density decreased rapidly, the dust remained dispersed in a filamentary structure that reflected sunlight with a bluish tint. This coloration came from extremely small particles, the size of smoke grains, formed by the rapid condensation of the ejected material. It was another proof that the event had been short-lived but of enormous energy. Scientists from the Institute of Astrophysics of Andalusia detected an even more intriguing detail. In the hours following the outburst, the comet showed periodic brightness variations that coincided with its 12-hour rotation. This indicated that part of the surface was still active, releasing gas intermittently. It was as if the comet had fully awakened after the outburst, breathing at regular intervals as it cooled. The interest in the community grew so much that several observatories allocated additional time to follow its evolution. Even telescopes originally dedicated to the search for exoplanets, like TESS, began recording light curves to analyze the luminosity changes. The combined data allowed for the construction of a temporal model of 3I Atlas's behavior during the following days. The conclusions were astonishing. The comet released most of its gas in the first 36 hours after the outburst, and then its activity stabilized at lower levels. At the scientific conferences in November, researchers repeated the same phrase: "We have witnessed the most documented event in the history of cometary astronomy." Never before had such a broad observation network been coordinated. Terrestrial telescopes, space telescopes, and solar probes working together to monitor a single object. This cooperation turned 3I Atlas into a symbol of international collaboration and a case study for future detections. The emotional impact was also palpable. In interviews and publications, astronomers spoke with a mixture of respect and wonder. Dr. Karen Meach, a veteran in the study of Oumuamua and Borisov, said something that resonated with the entire community: "This comet reminded us why we do science. Because the universe always has the last word." Her phrase went viral on scientific social networks, accompanying images of the comet taken by amateurs worldwide. Space agencies leveraged the media attention to announce new programs dedicated to interstellar objects. NASA proposed accelerating the development of the Comet Interceptor mission, designed to position itself at a strategic point and await the passage of a future visitor. ESA, for its part, initiated studies to incorporate instruments capable of responding in less than 24 hours to future detections. In both cases, 3I Atlas served as a catalyst for a new generation of interstellar exploration. In the following months, scientific articles began to fill specialized journals. The Astrophysical Journal, Nature Astronomy, and Astronomy and Astrophysics published issues dedicated exclusively to the event. The conclusions varied in details, but all agreed on one point. 3I Atlas demonstrated that interstellar comets are not mere passive fragments, but active bodies that conserve internal energy for millions of years. That energy, when interacting with a star, can release natural spectacles as intense as they are unexpected. In time, the media fervor gave way to scientific reflection. Astronomers knew the comet would soon disappear, but its legacy was already secured. The unexpected event became a lesson in cosmic humility. It reminded us that, even with the most powerful telescopes, the universe always holds surprises. And when scientists reviewed the final images of the comet, moving away with its diffuse tail fading among the stars, they understood they had witnessed something unrepeatable. A visitor from another world that for an instant showed us how little we still understand about the matter that travels between the stars. When the dust of the unexpected event began to settle and telescopes resumed their normal monitoring, scientists focused their attention on an inevitable question. How was 3I Atlas truly different from the two previous interstellar visitors, Oumuamua and 2I Borisov? The comparison was not just a historical exercise, but an opportunity to trace the evolution of our understanding of objects arriving from other stars. Each of these bodies had defied the expectations of its time. Together, they outlined a new field of study within modern astronomy. The first visitor, 1I Oumuamua, was detected in 2017 by the Pan-STARRS Observatory in Hawaii. Its fleeting passage left more questions than answers. Unlike 3I Atlas, it showed no visible coma or tail. Its brightness varied irregularly, suggesting an elongated shape or perhaps a highly reflective surface. It traveled at more than 87,000 kilometers per hour and left the solar system before telescopes could obtain high-resolution images. The absence of cometary activity led to the belief it was a rocky or metallic fragment, perhaps a piece detached from a forming planet. However, its non-gravitational acceleration generated controversy. Some scientists suggested it could be expelling gas subtly, while others defended the hypothesis of solar radiation pressure on an unusually thin surface. 2 years later, 2I Borisov appeared, discovered by amateur astronomer Gennady Borisov in Crimea. Unlike Oumuamua, this one did show a classic tail and clearly cometary behavior. It contained large amounts of water and hydrogen cyanide, indicating a composition similar to Oort cloud comets. Its passage allowed for the first study of the chemistry of an interstellar comet with modern instruments. However, Borisov partially fragmented upon approaching the Sun, demonstrating its structure was fragile and porous. And then came 3I Atlas. Its discovery 8 years after Oumuamua combined characteristics of both predecessors, the hyperbolic trajectory of the first and the cometary activity of the second, but with unprecedented structural resilience. Researchers soon understood that 3I Atlas was not simply another interstellar visitor. It represented a new type of object, denser, more complex, and with a chemical composition different from anything observed before. Comparing the 3 cases allowed for the tracing of a surprising evolution. While Oumuamua revealed that solid fragments can travel between stellar systems, and Borisov demonstrated that comets can do so too, 3I Atlas, in contrast, showed that these travelers can be much more active and stable than previously imagined, capable of surviving intense solar radiation and responding with controlled dynamics. In a way, each object expanded the definition of what we understand as interstellar matter. Astronomers also analyzed the entry velocities. Oumuamua moved at 26 km per second relative to the Sun, Borisov at 32, and 3I Atlas reached 35. This progression suggested the 3 came from distinct galactic regions with independent dynamic histories. Models from the Harvard-Smithsonian Center indicated that 3I Atlas likely originated in a zone with high stellar density, perhaps an open cluster where gravitational interactions frequently eject minor bodies into interstellar space. This provenance fit with the composition rich in carbon dioxide and the absence of water, an environment so cold that water would not have condensed as ice, but CO2 would. The differences were also evident in the internal structure. Oumuamua, without cometary activity, was probably a compact fragment of rock or metal. Borisov, fragile and volatile, resembled more the Oort cloud comets. 3I Atlas situated itself at an intermediate point, dense enough to resist heat, yet still capable of releasing gas and dust. This combination made it a natural hybrid, a bridge between interstellar asteroids and active comets. Some researchers even proposed that the 3 objects represent distinct stages in the evolution of bodies ejected from their systems. First solid and dry, then fragile and icy, and finally compact structures that conserve exotic gases. The contrast in behavior was also instructive. Oumuamua went unnoticed until it was already moving away. Borisov offered brief observations, but sufficient to confirm its nature. 3I Atlas, in contrast, was followed for months before its perihelion and throughout its encounter with the Sun. This complete coverage allowed for the observation of its activity in detail, from the brightness increase to the directed ejection and the subsequent unexpected event. Thanks to this, the scientific community could elaborate a dynamic portrait of its thermal life and death. In terms of chemical composition, the comparison was equally revealing. Oumuamua showed a flat, reflective spectrum without traces of gases. Borisov contained water, cyanide, and ammonia in proportions similar to local comets. 3I Atlas, for its part, exhibited an absolute dominance of carbon dioxide and carbon monoxide with traces of methane and complex organic compounds. This radical difference implied that each formed under distinct chemical conditions, reflecting the diversity of planetary environments in the galaxy. Researchers from the University of Cambridge proposed a unifying model. Interstellar objects would be the natural product of the evolution of young stellar systems. During the formation of giant planets, many minor bodies are ejected by gravitational interaction and wander the galaxy for millions of years. Some, like Oumuamua, lose their volatiles and become rocky fragments. Others, like Borisov and Atlas, conserve ice and gas. When they finally cross the solar system, they become chemical messengers that allow us to analyze the original materials of other suns. And 3I Atlas contributed something more: the demonstration that these travelers are not static, but can change during their galactic journey. Cosmic radiation, collisions with interstellar particles, and passage through dust regions alter their surface, creating hardened layers and provoking chemical metamorphoses. That galactic skin, hardened and bright, explained its high reflectivity and its capacity to resist solar heat. In a certain sense, the comet had been forged by the journey itself, molded by the energy of the void, until it became almost immune to destruction. Astronomers also noted a temporal pattern. The three objects were detected with just a few years of difference. This fueled the hypothesis that the transit of interstellar visitors is much more frequent than believed. Galactic dynamics studies estimate that on average, an object of size similar to Oumuamua crosses the solar system every year, although most go unnoticed due to their small size or lack of brightness. The arrival of 3I Atlas confirmed that with new observation technologies, we are entering an era where these visitors will cease to be rarities and become a common phenomenon. The comparison between the three also offered a lesson on technological evolution. In 2017, the available instruments barely allowed Oumuamua to be followed for 2 weeks. In 2019, Borisov was observed for months with terrestrial telescopes. And in 2025, 3I Atlas was monitored simultaneously by the James Webb, Hubble, the Solar Orbiter, and a global network of observatories. Each visitor arrived with a more advanced generation of tools, making it possible to capture details unthinkable just a few years prior. If a fourth interstellar object appears in the coming years, it will be received with probes prepared to intercept and study it up close. On a conceptual level, the comparison also changed the way scientists define the solar neighborhood. Before 2017, interstellar space seemed a distant frontier. After 3I Atlas, that frontier became permeable. We understood that the solar system is not an isolated bubble, but an open region where matter from other stars continuously enters and exits. Each visitor brings with it a sample of the chemical processes occurring in other systems, turning interplanetary space into a meeting point of worlds. NASA astronomers summarized that idea in a simple phrase: the solar system is a way station within the galactic highway. 3I Atlas was perhaps the most striking traveler to stop briefly at that station. Its extreme behavior, its resistance to the sun, and its controlled activity showed a perfect equilibrium between destruction and survival, a natural metaphor for cosmic evolution itself. As the comet moved away, leaving behind the sun's glow, scientists reflected on what this sequence of discoveries had meant. Oumuamua taught us to look carefully. Borisov showed us the composition of distant worlds. And 3I Atlas allowed us to witness the direct interaction between matter from another star and our own sun. Each one expanded a chapter in the history of human knowledge, and together they reminded us that the galaxy is not empty, it is full of silent travelers crossing space, carrying with them the secrets of their origins. From humanity's earliest records, the sun has been a symbol of life and destruction, the source that warms the earth and simultaneously the power that can disintegrate any body that comes too close. For astronomers, however, the sun is also a laboratory. Its light, its wind, and its magnetism become tools that reveal the nature of objects venturing into its domain. In the case of 3I Atlas, this interaction was fundamental. The passage of the interstellar visitor in front of the star allowed for the understanding of aspects that would have remained hidden if it had only been observed from a distance. When the comet approached within 1.4 astronomical units, solar radiation began to alter its molecular structure. Every photon striking its surface triggered a chemical reaction. The spectra obtained by the James Webb showed a phenomenon of photodissociation. The comet's complex molecules broke upon contact with ultraviolet light, releasing atoms of carbon, oxygen, and nitrogen. This process generated the faint green light surrounding the comet, an unequivocal signature of the solar impact. The sun, in that sense, acted as a magnifying glass that made the real composition visible. The solar wind, a continuous stream of charged particles, played an even more dramatic role. As the comet ventured into the inner system, the wind's protons collided with the gases expelled from the coma, creating microscopic shock waves. The solar orbiter's instruments registered these perturbations in the local magnetic field, evidencing that the comet's atmosphere had become a tiny shield resisting the solar flow. It was a silent duel between interstellar matter and the sun's energy, an interaction no other comet had protagonized with such intensity. In the plasma dynamics models developed by ESA, it was observed that the solar wind not only pushed the tail of 3I Atlas but also molded its internal structure. The charged particles induced electrical currents in the gas cloud, causing the tail to bifurcate. That division, visible in high-exposure images, revealed the existence of two distinct components: a dust tail formed by neutral particles reflecting sunlight, and an ionic tail composed of excited gas following the lines of the solar magnetic field. The result was a perfect choreography, a double flow responding simultaneously to gravity and magnetism. Scientists leveraged this phenomenon to study how the solar wind varies at different distances from the Sun. By analyzing the orientation of 3I Atlas's tail, they could measure the local plasma velocity with a precision previously only achievable with direct probes. In other words, the comet served as a natural diagnostic instrument. Where the solar wind was denser, the tail curved. Where it was weaker, it extended straight. Thanks to this, astronomers obtained a three-dimensional map of the wind structure around the ecliptic. But the Sun's role was not limited to acting on the comet's external environment, it also transformed its interior. As energy slowly penetrated beneath the hardened crust, the heat generated tensions that provoked the periodic release of gas. Every pulse of activity observed in the weeks before perihelion was a direct response to the increase in solar radiation. Without the Sun, 3I Atlas would have remained dormant, invisible, just another fragment in the interstellar darkness. It was the proximity to the star that awakened it, revealing its true character. In a way, the Sun functioned as a cosmic catalyst. It did not destroy the visitor but forced it to show its structure, its chemistry, and its resilience. The James Webb observations demonstrated that the Sun's infrared radiation did not penetrate beyond a few centimeters, which allowed the nucleus to remain stable. This equilibrium between exposure and protection defined the comet's entire behavior. The heat was strong enough to generate activity, but not so much as to disintegrate it. It was a perfectly calibrated dance of energy. Researchers from the Institute of Astrophysics of Andalusia described the situation with a precise metaphor. The Sun is the mirror that undresses comets. Every ray reveals distinct layers. Every interaction shows a new element. In the case of 3I Atlas, that reflection was double. On one hand, the comet taught us how interstellar matter behaves in front of a star like ours. On the other, it offered us information about the Sun's own nature, its radiation, its wind, its capacity to transform cold bodies into luminous beacons. The study of 3I Atlas also allowed for the examination of the heliosphere's limits, the plasma bubble surrounding the solar system. When the comet crossed that boundary, its interaction with the solar wind became detectable. Scientists at the Goddard Center observed that the density of ions in the coma increased as the comet approached, an effect of compression caused by the wind's dynamic pressure. This phenomenon helped calibrate particle dispersion models and allowed for the confirmation of indirect measurements about the real extent of the inner heliosphere. On a chemical level, the Sun acted as a laboratory of photonic reactions. Ultraviolet radiation broke molecular bonds and generated free radicals that then combined to form new compounds. Hubble spectra showed traces of formaldehyde and acetylene that were not present before perihelion. These products were the result of reactivity induced by solar heat, meaning the comet underwent a small chemical transformation during its passage. In a way, the Sun cooked the comet's surface, altering its chemistry and leaving a new spectral signature that astronomers could trace. The event also provided lessons on the physics of sublimation. In terrestrial laboratories, scientists simulated perihelion conditions using vacuum chambers and ultraviolet light. They discovered that mixtures of carbon dioxide and carbon monoxide subjected to rapid temperature variations can generate directional jets exactly like those observed in 3I Atlas. The Sun, with its constant flow of energy, acted as the detonator of these natural microgeysers. Each outburst was a predictable physical response to a thermal impulse, a reminder that even the most spectacular phenomena can be explained by simple laws of thermodynamics. For solar astrophysicists, the visit of 3I Atlas was also an unexpected opportunity to study how comets contribute to interplanetary dust. The ejection of material towards the Sun detected during perihelion temporarily integrated into the zodiacal dust stream. By observing its dispersion through the solar orbiter's sensors, researchers calculated that a minimal fraction of that dust would remain orbiting near the star for decades. It is likely that in the future, part of this material will mix with Mercury's atmosphere or join the meteoroid stream crossing the ecliptic. Thus, even after leaving, 3I Atlas will leave a microscopic imprint on our system. Ultimately, the Sun was the silent protagonist of the entire story. Without its heat, the comet would have remained mute. Without its wind, we would not have seen its tail. Without its magnetism, we would not have understood the interaction between matter and plasma. Every piece of data astronomers extracted was born from that direct relationship. The sun not only illuminated the comet, it revealed it, transformed it, and turned it into a messenger that brought us information from beyond the Milky Way. When the observations concluded and 3I Atlas began its retreat into darkness, many scientists realized something essential. The encounter had not been a simple cosmic accident, but a demonstration of how stars influence their environment and the bodies passing through it. The interaction between the sun and the comet was a microcosm of processes occurring throughout the galaxy. Stellar energy acting upon primordial matter, molding it, illuminating it, and finally, returning it to the void with a new identity. The sun, so familiar to us, became a tool of discovery for understanding worlds we will never see up close. And 3I Atlas, with its brief but intense journey, was the perfect witness to that power. In the glow that enveloped it, in the wind that battered it, and in the silence that followed its departure, remained the proof that our star not only gives life, it also reveals the secrets of the universe. After the perihelion, when 3I Atlas began to slowly move away from the sun, the comet's story entered a quieter phase, but one no less revealing. Many thought the spectacle was over, that the activity would diminish until it disappeared completely. However, telescopes continued detecting signals demonstrating that the interstellar visitors still had much to tell. What happens after perihelion, that stage where a comet begins to cool and its brightness fades, is as important as the moment of maximum activity, because in it the physical and chemical consequences of the encounter with the star are defined. As the comet moved beyond 1.6 astronomical units, the intensity of solar radiation decreased, and the flow of gases gradually reduced. The coma began to contract, and the spectra showed a progressive decrease in the lines of carbon dioxide and carbon monoxide. But the surprising thing was that even with less energy, the comet continued showing intermittent peaks of brightness, like small heartbeats repeating every 12 hours. Researchers concluded these variations corresponded to the last active vents on the surface, zones that kept releasing gas trapped in deep cracks. The James Webb, which continued observing the comet from its position at Lagrange point 2, detected a drop in surface temperature to 120 Kelvin. However, the infrared sensors registered a curious phenomenon. The comet's interior still retained residual heat. Simulations showed this heat would take weeks to dissipate completely, explaining the prolonged activity. In other words, 3I Atlas was cooling slowly from the inside out, like a stone that still holds the fire from its last contact with the sun. The cooling process had visible effects on its appearance. The main tail began to stretch, lengthening over 300,000 kilometers, while a second, fainter tail, formed of fine dust, slowly separated from the main axis. Astronomers noted that the color of the coma was changing. The intense green of perihelion transformed into a pale blue tone, a product of the decrease in ionized cyanogen. This color change was documented precisely by Hubble, which managed to capture images of the comet already in the descending phase of its activity. Spectral analyses conducted at this stage confirmed that the gaseous composition was also changing. Carbon dioxide remained the main component, but traces of methane, ethane, and ammonia began to appear. These molecules, more stable at low temperatures, emerged as the more volatile gases were depleted. This phenomenon allowed for the reconstruction of a kind of chemical stratigraphy of the comet. Each phase of its journey revealed a distinct layer of its interior. The perihelion had released the superficial gases. The post-perihelion, in contrast, was showing the heavier, older compounds. At the Planetary Science Institute in Tucson, researchers compared the observations of 3I Atlas with models of cometary evolution. They discovered the object had lost less than 3% of its total mass during its passage through the solar system. This figure was surprisingly low, considering the intensity of the perihelion. While local comets like Ison or Lovejoy disintegrated completely upon approaching the Sun, 3I Atlas barely suffered superficial erosion. It was the definitive confirmation of its compact and dense nature, a nucleus capable of resisting extreme thermal forces. The comet's rotation also changed after perihelion. Photometric observations from La Silla showed its rotation period had reduced from 12 to 10.8 hours. This acceleration was a direct consequence of the gas ejection during the outburst. Each jet acted as a small thruster, transferring angular momentum to the body. Although the change seemed slight, it was enough to modify the dynamic equilibrium of the nucleus. Some astronomers suggested that if the comet continued accelerating, it could fragment in the future when the tensions exceeded the resistance of its structure. The orbital dynamics team at the Jet Propulsion Laboratory calculated the object's new trajectory using the post-perihelion measurements. The result confirmed that 3I Atlas followed a hyperbolic orbit with an escape velocity of 35 kilometers per second. This meant it would never return. Once its journey through the inner solar system was completed, it would be lost again into interstellar space, heading towards the void between the stars. Within a few months, its brightness would fade below detection limits and its trace would disappear from the visible sky. But before saying goodbye, the comet left one last gift for scientists. In December 2025, the solar orbiter detected a diffuse cloud of particles in the trajectory it had followed weeks before. This cloud, composed of dust grains smaller than 1 millimeter, corresponded to the material expelled during the outbursts after perihelion. By analyzing its dispersion, researchers could estimate the total mass of dust released and determine its contribution to interplanetary dust. For the first time, it was measured how an interstellar comet in its departure phase could modify the environment of our own system. Astronomers also took advantage of this period to study the nucleus's reflectance. Without the interference of intense solar glare, it was possible to measure its albedo with greater precision. The results confirmed that 3I Atlas had a surprisingly reflective surface with an albedo close to 0.6, similar to some metallic asteroids. This property explained why it had resisted the sun's heat without melting completely. Its surface acted as a natural mirror, reflecting most of the incident radiation. In the laboratories of NASA and ESA, scientists processed the last observations from the James Webb. The infrared spectra revealed that the nucleus's temperature kept descending, finally stabilizing around 90 Kelvin. At that point, all activity stopped. The comet had returned to its original state, a frozen, silent body, traveling towards the darkness. Thermal models showed that the cooling not only affected its surface but also provoked internal contractions. These changes may have resealed the fractures opened during perihelion, restoring the nucleus's integrity. It was a process of cosmic healing, the comet mending after the encounter with the sun. Astronomers were fascinated by the idea that after this episode of extreme heat, the object could preserve its structure and continue its journey for millions more years. Meanwhile, public attention began to wane. The headlines that weeks earlier spoke of the comet that defied the sun gave way to other news. But for the scientific community, the work was just beginning. The data collected during the post-perihelion became a mine of information on the physics of cooling and the chemical evolution of comets. It was the first time an interstellar visitor had been observed so closely throughout its entire cycle: approach, encounter, and retreat. By mid-January 2026, telescopes registered the last detectable images of 3I Atlas. Its brightness had fallen to magnitude 18, too faint for visual observation. On the trajectory charts, an almost straight line marked its definitive exit from the ecliptic plane. No one would ever see it again. However, the comet's legacy would not be lost. The data stored in the archives of the James Webb, Hubble, and Solar Orbiter would be studied for decades. For astronomers, the post-perihelion of 3I Atlas was the perfect closure of a story that combined resilience, transformation, and knowledge. It was the confirmation that interstellar objects not only survive contact with stars but also evolve through it. On its inbound journey, the comet arrived cold and dormant. On its outbound journey, it departed transformed, with a different surface and a chemical signature modified by the energy of our sun. When it finally disappeared from the telescopes, a feeling of emptiness ran through the observatories. The silence it left behind was the natural echo of an event that had lasted months, but it was also the beginning of a new stage in astronomy, the certainty that at some point in the future, another interstellar visitor will again cross our sky, and thanks to 3I Atlas, we will be ready to receive it. When the last signal from 3I Atlas disappeared from the reach of telescopes, it became clear that its passage had marked a before and after in the history of modern astronomy. It was not just another visitor that crossed the solar system, but a case study that redefined the boundaries of what was believed possible in cometary physics. The months of observation, the collected spectra, the solar wind measurements, and the high-resolution images formed an unprecedented archive, a legacy that would change our understanding of interstellar objects and, in a broader sense, of galactic evolution itself. The first aspect of that legacy was the confirmation of the chemical diversity of the cosmos. Before 3I Atlas, astronomers knew two examples of interstellar bodies, Oumuamua and Borisov. Both had provided clues, but their information was incomplete. 3I Atlas, in contrast, revealed a composition dominated by carbon dioxide, carbon monoxide, and complex organic compounds with barely traces of water. This proportion altered the models of comet formation. It meant that in other planetary systems, temperature and pressure conditions could generate icy bodies very different from those in the Oort cloud. It was empirical proof that the universe does not follow a single chemical recipe. Each star cooks its worlds differently. The second fundamental contribution was the comet's structural resilience. No body of interstellar origin had withstood the sun's heat so closely without fragmenting. The James Webb data showed that the nucleus of 3I Atlas had a density of around 1.5 grams per cubic centimeter, more than double that of typical solar system comets. Its reflective surface and hardened crust protected it from disintegration. For astrophysicists, this discovery demonstrated that time and cosmic radiation can turn a fragile body into an almost metallic structure, a kind of fossil comet that has survived millennia of travel between the stars. The third legacy was methodological. The coordinated observation between NASA, ESA, the James Webb, Hubble, the Solar Orbiter, and dozens of terrestrial observatories established a new standard for the study of cosmic phenomena. For the first time, an interstellar object was followed from beginning to end, from its approach to its exit. This coordination allowed for the construction of an integrated database spanning from the infrared to the ultraviolet spectrum. In the coming years, this information will serve as a reference for designing interception missions for future similar objects. 3I Atlas, without intending to, became the model of operation for 21st century astronomy, global, collaborative, and based on shared data. In the field of solar physics, the comet offered a unique opportunity to study the heliosphere from within. The interaction between its ionized gas and the solar wind allowed for the tracking of local variations in plasma density and velocity, something impossible to measure directly. Thanks to 3I Atlas, scientists could map the sun's magnetic field in a region where only theoretical models existed before. This information not only improved the understanding of solar activity but also helped calibrate instruments to be used in future missions to Mercury and inner space. The legacy of 3I Atlas also reached prebiotic chemistry. The observations from Webb and Hubble detected complex organic compounds like formaldehyde, ethane, hydrogen cyanide, and small traces of aromatic hydrocarbons. These molecules are the basic building blocks of life, and their presence in an interstellar body suggests that organic chemistry is not exclusive to our cosmic neighborhood. Astronomers began to consider the possibility that interstellar comets could act as natural vehicles for molecular transport between stellar systems. They do not bring life, but the fundamental ingredients for it to arise. Each time an object like 3I Atlas crosses a star, it could sow fragments of its chemistry along the way. Another important consequence was the advance in the understanding of cometary thermodynamics. The data demonstrated that the activity of 3I Atlas did not depend solely on distance to the Sun, but on its internal thermal memory. The comet showed delayed outbursts weeks after perihelion, driven by the release of gases that had remained trapped during its heating. This finding led to a revision of classical sublimation models and ushered in a new paradigm. Comets are dynamic systems with independent thermal layers capable of releasing energy gradually. Cometary physics, until then based on observations of solar system bodies, had to adapt to an interstellar scale. The educational and cultural impact of the event was equally profound. The image of the comet, with its greenish glow in front of the Sun, spread throughout the world, inspiring documentaries, educational programs, and a renewed curiosity for science. Space agencies leveraged the global attention to promote astronomical research as a collective effort of humanity. In schools and universities, students learned that a small fragment of ice from another star had revealed secrets about the origin of the cosmos. 3I Atlas became a symbol of shared knowledge, a reminder that science knows no borders. In technological terms, the experience drove improvements in early detection protocols. The Pan-STARRS Observatory and other automated search systems updated their algorithms to identify hyperbolic trajectories more quickly. Now, any object with a velocity superior to the solar escape velocity is immediately catalogued as potentially interstellar and prioritized for observation. Thanks to these improvements, it is expected that future visitors can be studied even before entering the inner system, allowing for close-approach mission planning. The scientific community also reflected on the role of chance. If the comet had passed a few degrees further from the ecliptic plane, its trajectory would have been outside the visual range of the main observatories. Its discovery was partly a fortunate coincidence, but also a demonstration of technological preparedness and human cooperation. Every spectrum, every image, every analysis was the result of decades of investment in science and in the collective curiosity that drives humanity to look beyond. In time, the legacy of 3i Atlas transformed into a roadmap for the future. NASA and ESA announced plans for a joint mission called Interstellar Probe Pathfinder, whose objective will be to intercept the next detected interstellar object and analyze it with high-resolution instruments before it leaves the solar system. Without 3i Atlas, this idea would have seemed premature. With it, it became inevitable. On a philosophical level, the passage of 3i Atlas also changed the way humanity sees itself in the universe. For the first time, we had direct evidence that fragments from other stellar systems cross ours regularly. We are no longer isolated observers, but participants in a continuous exchange of matter between stars. Every interstellar visitor is a cosmic letter sent from an unknown place, written with the ink of elements born in alien suns. In the months following its disappearance, scientists continued publishing derived studies. Some focused on thermal evolution, others on isotopic proportions, and several more on the implications for planetary formation, but all shared the same recognition. 3i Atlas had been the most complete visitor, the best observed, and the most revealing in modern history. And although its light is no longer seen in the sky, its legacy continues to shine in the laboratories, in the simulations, and in the imagination of those who seek to understand the universe. Every piece of data archived in the servers of the James Webb or the Solar Orbiter remains an open window to that moment when a body from another sun crossed ours, resisted the fire, exhaled its history, and was lost again in the darkness. Perhaps at some point in the future, another interstellar object will appear again, and when that happens, scientists will know exactly how to observe it, how to measure it, and how to understand it. Because once, in the year 2025, a comet named 3i Atlas taught us that even the most ancient ice can become light when it encounters a star.